Even hear you.
Okay.
Okay, so I think we are set to go, right?
Yes, we are. Yeah.
Okay, so good evening again to our second session uh, of the first day of AIR conference 2021. Now, sorry for the slight delay because of unforeseen circumstances. So it gives me great pleasure to introduce Professor Sunil Agarwal as the speaker for this session. And Professor Sunil Agarwal obtained his BTech from IIT Kanpur in 1984, MS from Ohio State University in 1986, and PhD from Stanford in 1990. And he is currently a professor of mechanical engineering and professor of rehabilitation and regenerative medicine at Columbia University. And he'll be his area of research is gait training of elderly, stroke patients, balance for children, Parkinson's patients, etc. He's a fellow of the ASME and has published over 450 papers. So, Professor Agrawal, welcome, and please make your presentation.
Well, first of all, thank you, Ashish. Can you all hear me?
Yes.
And the video and the video is fine as well, right?
Yes, video is perfect.
Okay. Okay. So I'm so sorry for the technical glitch. I really apologize for keeping you all waiting for such a long time. So as Ashish mentioned, I got actually a degree from IIT Kanpur, so I'm very proud of that, and had a number of years that I stayed on campus. So those are fond memories for me when I was a student there. So I'll tell you a little bit about some of the work that I do. I've been trained into robotics, as many of you have been trained. And most of my earlier work was in terms of parallel robots, kind of looking at how do you kind of design parallel actuated robots and so forth. And so it's been a lot of fundamental robotics work for many years. And more recently, in the last sort of 8 to 10 years or so, I sort of focused more on how you can use robots to help people to improve their quality of life, right? And we know that all of us, as we are growing old, we encounter number of issues. We are all getting older, our sensory system decays, our motor system decays, or there are people who have neurological diseases. I mean, Parkinson is one of them, or there may be incidences of stroke, or there are children who are born with cerebral palsy, or people have ALS and so forth. So there are many situations where we feel that robotics can be a tool to help improve or regain function. And I'm going to share with you some of these experiences that I've had over the years. So please bear with me. Hopefully I can share some of those studies with you. So this is a quick overview of some of the things that we are doing at the Road Laboratory here in Columbia. And as you'd expect, that these are very multidisciplinary projects and involves, of course, graduate students, PhD students, postdoctoral researchers, but also we have a large medical team that sort of works with us. And these are people from the rehab medicine, from neurology, orthopedic surgery, or maybe geriatrics and others. And the fundamental idea here is that whether you are young, whether you are old, your brain has the ability to learn, right? And often the learning is sort of facilitated by sort of working with physical therapists who sort of manipulate the different parts of the body in the hope that you can sort of get back some of the functions. And as you can think about, the function is sort of related to what's happening at the brain level, the spinal cord level, right? I mean, the spinal cord would sort of send signals to your muscular system, and then the information sort of get back to the brain. So it's a closed loop system between the movement that you see at an effector level and what's happening in the spinal cord and the brain and the musculature. So a lot of what we are doing here is we are saying, can we really retrain the brain or the spinal cord through these repetitive exercises or that you do with movements? So again, I mean, this is a broader philosophy, and of course, there are many researchers all around the world who kind of work on this premise. And in fact, Dr. Ashish Datta himself kind of works a lot into these kinds of problems, and I'm sort of familiar with some of these. So what you see here are a bunch of different issues. For example, stroke, people who have, let's say, a one-sided impairment because of a stroke at some part of their brain. Or you can have, let's say, people with children with cerebral palsy, or maybe we have Parkinson patients, older individuals. But what our lab really focuses on are different functions of the human body, whether that is walking, whether the stair climbing, whether you're turning your head to see things, or you're looking at, let's say, upper body. So what I'll show you here, how do we look at functions? And this could be very specific functions, whether you're looking at the trunk control, arm control, or leg control, or the balance, and so forth, and how we can facilitate some of that through robotics. So we use a number of tools, and most of these robots that you see are actually designed by our students in the laboratory. And these are sort of really, we do not sort of buy anything from outside except for the motors and the electronics and the control system that would sort of go along with it. But all of these devices are eventually integrated and programmed and tested in our laboratory. So I'll walk you through some of these examples as we go along. So among some of these examples that you see here, I'm going to focus on 3 or 4 of these in the interest of time. And hopefully you can sort of ask some questions later on as they come to your mind. So I'm going to talk about some of the pediatric applications today. And of course, I mean, we look at elderly individuals, stroke, adults, and so forth. But I deliberately chose the children as the focus of the work today. So you may be wondering why robotics? And can you all still see the screen and everything is sort of being transmitted okay?
Yeah, everything is fine.
Okay, wonderful. So then you must be wondering why robotics? And some of our take on this is robotics can help retrain movements by modulating forces. Okay, and this mimics how physical therapists do, right? So often in robotics, we talk about motion control, force control. And what we are really saying here is that we can think about the force control aspect of robotics. And that force now is being applied to the human body in some specific area. I mean, whether it's a leg, whether it's a trunk, whether it's arms or the neck, right? And so we want to sort of see how we can use the force control aspect of robotics to help retrain movements. Now, also, when you think about movement training, right? So it's not just a matter of we put an individual into a machine, and the person is now starting to move better or so forth, right? I mean, you have to acquire the skill of movement, right? And acquiring a skill is different from just assisting the person to sort of move, right? So what you're really doing is you are retraining the brain slowly over a period of time, and so that the person becomes skillful at that particular task. So you have to use a lot of theory that you learn from human motor learning and the way people learn into the process. And we'll talk more about it as we go through this. Also, we all know that robots can quantify progress, right? And all of us are aware that robots have sensors in them, right? And it can record, and you can also put other auxiliary sensors on the human body, whether that is muscle, whether the ground reaction force or movement data. And some of that information can be stored, and you can sort of look at these across sessions to see what kind of changes have been done. So this is a new project for us, but it is sort of derived from many of the previous projects. If some of you are familiar with our project, then so let me kind of motivate this particular application. So these are children with CP. So CP is called cerebral palsy. And just to give you a quick insight into the cerebral palsy is something that it's a neural insult that the child faces early on at birth. And this is a non-progressive disease, right? So whatever happened once, that is there and remains throughout the life of the children. And as a result of this cerebral palsy, that may have a lot of ramifications in terms of motion, in terms of speech, in terms of visual, and so there are many aspects that get affected by CP. But what we are focusing here is one specific aspect, which is the trunk control, right? So we call it trunk control. So here's an example of a child who has a severe CP, and we put him on the floor, right? Normally, when you are on the floor, you can kind of sit straight, just like this child up here, this caricature up here. But these children are not able to sit straight, right? And they would essentially sort of fall down to the floor. And as you can see, this child here, he's not able to sort of keep his trunk straight. And as you can expect here, not being able to sit affects your quality of life in so many different ways, right? You can't interact with somebody who's talking to the child, or the child cannot go to school and learn, and the child cannot feed himself or herself, right? Because they're sitting in a chair, but they're not being able to keep straight. So thus this inability to move the trunk is a disaster for this child over a period of time. So the question is, what would a therapist do, right? And if you think of, let's say, this individual who is behind the child, right? He can, at the most, sort of help stabilize the child in a vertical position, right? So that's good. I mean, the therapist has actually two hands, right? But now if I had to think about training of the child, right? So training the functional task of the child, you really need many hands, right? So you see a single therapist here, but you may, require a lot more, because you have to manipulate the body in certain areas. You have to challenge the child. You have to sort of support the child. So some of these things are almost impossible to do for a physical therapist, right? So what you really need is a magical therapist which has got many hands to that. Okay, and these hands, some of them may apply force on the child. Some of these may engage the child in different tasks, and also sort of see how the child is doing, so that way you can make a higher level decision as to what to do with the child now at this time. So what we designed here is something called a trunk support trainer, right? And conceptually, it's a very simple idea. It is a little belt that you can put on the trunk of the child. And often when people have, let's say, trunk inability, there would be a certain region of the trunk, if you support, then they would be able to keep their posture straight. But as you lower down the support, the child will again sort of buckle, like what you see out here, right? So essentially what you can really do is lower this belt across training, depending on how the child is able to sort of improve their ability. So now let's think about, what does the robotics do, right? So this belt here is attached to the trunk of the child. You can move the belt wherever you want to, depending on the current state of the child. But through this belt, there are 4 wires. Each of these wires are connected by a motor that you can see here on the frame. And what these 4 wires really do is create a little donut, right? So it's a force field around the child, right? So that you can see a little picture out here, this ring around the child. And this is really a virtual ring, right? And this virtual ring is created by controlling the tension in these 4 wires. And what you can do is you can create this virtual support. So think of this child who's kind of working with this physical therapist in different tasks. And what the therapist really is doing is trying to ask the child to go and reach for an object, and basically we're challenging the child to go much further away from this vertical equilibrium and do the task, right? So what you see here, this trust or the trunk support trainer really integrates a number of these different ideas. First of all, it integrates what is, many hands, right? It creates a virtual force field, right? It allows you to sort of look at the child and challenge the child to do different things. So it's an integration of both engineering or robotics along with physical training. And now what the therapist is really doing is he's actually playing with the child. He's actually challenging the child to move in different directions. I'll show you little videos later on. So some of the motivation for this particular work really came out from simple experiments that we did with healthy individuals, right? And you can see here that the two subjects here are sitting on a stool, and we are challenging them to go further away from the neutral position and do this task. So for example, she's putting these pegs in a hole. Okay, and what this donut-like force field is trying to do is, as she's becoming unstable, essentially it creates an external support. It's a virtual external support. Now, what was very interesting here is that if you were to train, let's say, an individual, okay, and these are all healthy individuals, if without this donut-like force field, right, let's say they were able to reach a certain anterior displacement, right? So how far can the trunk lean forward in order to sort of do the task? And what you can see here, there are two groups, the control group and the experimental group, right? And what we are showing here are two sets of data, pre and the post training. And in this case, training is a single session for about an hour. And what you see is that the control group, which was not given with any force field, they had a small change in terms of how far they can reach in the forward direction. But the experimental group, who was given with the force field, they were almost able to double their anterior reach, right? So essentially what it allows us to sort of verify that even healthy individuals like you and I, okay, we can actually benefit in terms of how much further we can reach from a neutral position through this kind of technology. So let's kind of go back to the children with cerebral palsy, okay? And so we actually recruited 4 children with cerebral palsy, somewhere in the age of 11 to 12 years, right? And they have really, so if you think of this trunk here, and these are kind of areas 1 through 6, depending on where you need support in order for you to be able to perform the task. Okay, and there is a assessment called SATCO, which allows us to assess where exactly you need trunk support. And also there is something called a gross motor function classification system, which says that these are children who are actually unable to walk by themselves, and so they need a wheelchair. There's a 3 and 4 mean, and we're looking at those kind of children. So instead of, it's a busy slide. I'm not going to sort of go through it much detail here, but I'm going to show you some videos here. And the training for these children were actually 12 training sessions. And in each of these training sessions, I mean, we played around with where the belt was and how much force field was there. And you will kind of see later on some of the videos of these children. So can you all see a video here? Ashish, can you see a video? Hello?
We can see the video.
Yeah,
okay,
we
wonderful.
can see. It's very clear.
Okay, wonderful, right? So here is a child, okay, who's being trained. As you can see, she's sitting on this bench. She has these 4 wires, and there's a therapist who's actually challenging the child to move and reach for the ball in different directions. And the therapist can essentially go forward, sideways, back, diagonals, and so forth, right? So let's see what happens to this child. When you say pre-training and the post-training, this is about training for an hour and a half, and these are 12 sessions of training. So let's kind of look at the pre-training and the post-training data for this child, okay? In the pre-training, you can see as you displace the child, she has a lot of difficulty, okay, to be able to balance herself, right? And she has to kind of, even though she's trying to control the trunk to come out in the neutral position, she has to really kind of use all of her limbs to be able to come there. And she has a bad posture on her neck and others. Now, if you look at the post-training, and in the pre-training, of course, I mean, these are no forces being applied through the belt because this is just the ability of the child. But if you look at the post-training, the child is able to go far away from the neutral and be able to come back, right? And she does it a lot very smoothly without a lot of inability to do that. Yeah. So let's go back to the look. So here is a video. I will let it play here. And basically, these are videos that you can actually see as a part of a supplement on a paper that has appeared in the TNSRE. And you can sort of obtain this from the TNSRE website. So all of these videos that are seeing here actually are included as a supplement of that particular paper. So here's a second child. You saw a girl in a previous video. He's a boy, and he also has these issues. He has a poor trunk control, and in this case, after the trunk has been controlled, now you can see the level of ability of this child and the way they are able to do the functional task while being able to. So what you can see, the child actually has a lot better control of his trunk. He's able to sit upright. He's able to do these functional tasks and so forth. Yeah. Okay. And so what I'm going to do, so these are some results. And what you see on the y-axis is the ability for the child to move in different directions. Okay. So if I look at the vertical as the 0 area, right, and you look at these 8 directions, forward, backward, sideways, and the diagonal direction, and see how much is the area change. And so this y-axis in centimeters square. On the x-axis is the number of training sessions, like 0, 1 through 12. Okay, and then there is a post-training that is 2 weeks later on, and then there's a follow-up, which is 3 months later on. And we wanted to sort of see how that training would change this outcome measure. Okay, and if you were to sort of really look at the different directions, this is the area. The white is the area before the training, and the brown one with the red boundaries is the area sort of after training. And you can see the child is able to increase their area of reach, and they are able to sustain some of that post-training and also can able to do the follow-up. So this is the paper that I was talking about. This has appeared in the journal, and there is all these videos that I showed you are a part of that particular journal. Also, we look at a different reaches of child. In fact, we have now a 5-year study. Okay, do a randomized clinical trial with 85 CP children, and the goal is to look at 2 groups of these children. One of them would be a trust-enabled training, while the other one would be the best practice currently. And we are going to blind all the outcomes to show what is the differences in terms of the effectiveness of this idea. Yeah, and this is a NIH project. This is a 5-year project for us through the NIH, along with one of my colleagues, Dr. Andy Gordon, who is who's a CP scientist. So let me kind of move on to another topic of for children. And we can come to all the questions and answers at the end of my talk here, and so we can assign some time for that. So just a little bit about children. Many of these CP children would have inability to be able to walk, right? And you can see 2 therapists kind of working with these children on a treadmill to have them sort of improve their walking function. And part of the motivation was here to look at how do you help these children to kind of learn walking. And this is a picture of a mother kind of helping the child, and you can see the typical mother would support the child at the pelvis level, right, to support if the child is falling down. And again, this is a very important part of robotics, because often we make robotics, which are sort of really, it's an exoskeletal kind of devices, which is wrapped onto the arms or the leg. But there we are facilitating the motion, but it's not necessarily a good tool for motor learning. And learning is all about that you have experiences, you make errors, you fail, and we allow you to retune your movement through those experiences. So, and in fact, this is a device, we call it a T-pad or tethered pelvic assist device. And the reason is that these are tethers connected to the pelvic device. And in fact, Vineet Vashisht, who is in the audience today with us, this was a part of his PhD work, which led to some of these designs. And with this particular device, you can really apply continuous force on the human body as they are walking. It could be intermittent forces, could be synchronized with gait events and things like that. And we'll see that we can use this device in lots of very clever ways. So this is a video of a child with cerebral palsy again, and there's something called a crouch gait. And as you can see, the child actually is not walking straight. He's walking with his knees bent, his hips bent, and so forth. And typically, crouch gait children have a lot of issues in terms of movements, of course, balance as well, but also it's kind of bad on their joints. Many of these children would actually have arthritis towards the later part of their life. And the question that we ask ourselves, how can we make these children walk more straight? And one of the things that we tried out was that what if I were to make it more difficult for these children while they're walking, right? And we do that by actually applying a downward force on the pelvis while they're walking. And part of the motivation is that when you are walking, you are moving your pelvis up and down in a cyclic fashion, right? So as you are moving your pelvis up, right, you have to use your extensor muscles on your legs, right, in order to sort of move yourself up. And part of the motivation was to retrain the strength of those extensor muscles. So what we really did is we had these children have about 10% body weight during the training. And of course, I mean, we changed the speed of walking and to challenge them more as the training went on. So let me show you the video of the same child before and after training. And this training was done over a 15-session period. And as you can see, the child is walking over ground after the training. And you can see a lot difference in terms of improvements in posture of this child. And the girl out here, her name is Jion, and she actually conducted this study along with the device that Vineet had developed. So this is what the training looks like. The child is walking on the treadmill, right? This is sort of two videos very early on in the training and later on the training. And you can see that early on, the child was walking very slow, not very confident and things like that. But by the end of the training, he was actually walking a lot faster, larger gait length, and so forth. Also, if I look at the ground reaction forces, one can actually show that he was actually generating these peak forces with the foot at the right instances of time. So 0% is when you have a heel strike, and about 60% is when you have a push-off. So actually, he was generating these nice peaks as opposed to earlier on where he did not have those peaks. So we are trying to sort of move these technologies to how we can use for overground walking. And so we have actually now redesigned our technology to have these wires attached to a rollator. And I'm just going to show you a video of somebody kind of walking. And they are still having those same belts with these wires, and all the motors are up here. There are several shortcomings in our previous design because we were actually using a camera system to know the feedback of the pelvic brace. But now what we do is we actually don't use cameras anymore, but we actually use the kinematics of the robot to do these kinds of calculations. And we have been able to validate this system to do a number of studies. And this is something that we are actually pursuing in terms of children with cerebral palsy who actually have something called a Trendelenburg gait, right? Because as you can see here, the children actually have a lot of upper body swing because of poor control of their hip muscles and so forth. So hopefully you can see some of these things in the future along these lines. So let me kind of move on to a third example. Okay, and in this case, part of the motivation here is that there are a lot of people who have got neck issues, right? And we know that people with ALS have those kinds of head drop. For example, those of you remember Stephen Hawking, he often would just kind of sit on the chair and he would be sort of slumped in the chair. He would not be able to sort of control the posture of his head. So we have been looking at various design of these neck devices. And in this case, this is a parallel manipulator which sort of connects between the shoulder and the head. And in between, there are these multiple chains, and these chains have been designed so that you get the range of motion of the head and be able to do various things with it. So this is a kind of a device which can either be active or passive. In this rightmost video, you can see a joystick which actually able to control the motors, and then that can actually control the head or so forth. And you can do a number of different studies in terms of understanding what the deficits are. And in this case, typically we look at the muscles from the neck and see how those muscles are sort of coordinated in these neck movements. And of course, if you have a head drop, then those muscles sort of work very differently than in healthy subjects. So there are a number of studies that we have published along these lines, and this is a study that we did for patients with ALS to look at what their how their head neck control got affected because of the disease. So we have actually used this in a number of different studies. So this first video, you can see the neck can be used as a joystick here, right? So typical joystick, we actually use a handheld joystick, right? But in this case, we are trying to see if I can use the neck brace as a way to control things, right? Maybe one application would be that if somebody is kind of flying a drone or something like that, or you are sort of doing sort of video gaming. So instead of using a hand, you can use the neck to sort of make these kinds of movements. So again, we did a comparison of the neck as a joystick versus the conventional joystick. This is a second video here where we have a patient with ALS, and we are actually using the active support from our neck brace to allow the person to kind of make these movements. So here there's an avatar on the screen who's actually making a movement, and we are actually using the neck brace to facilitate some of those movements. And this is actually great for patients with ALS who have not been able to sort of move their head by themselves, and this was sort of a great fun experience for them. And we have some projects right now to sort of look at these. Also, a number of people who have poor neck control, they would not have ability to move their limbs because of the lack of the muscle control. So we have some of these eye-head interfaces where we look at the eyes are used to track where the subject would like to move to, and then it's given a command to the head neck brace, and that way you can have a hands-free device to help people with ALS to be able to navigate themselves in different ways. Are you able to sort of see and hear me?
Yes.
Okay, well, that's wonderful. Okay, so what I'm going to do is kind of show you some potential things that we are doing right now. And this is sort of work in progress right now. And this one is actually to look at how do you strengthen the neck of persons, right? So somebody with a cerebral palsy, they may have a really poor neck control. And what in this case, what we're doing is there's an active resistance that you provide to the head while they're making these different movements. And as a result of working against the resistance, they're able to strengthen their the muscle activity in their neck. So there is a recent paper that we published into 2020 about some of these ideas of how to use resistive force fields for head neck training in patients with poor head neck control. So let me kind of switch gears here. This is another project in our laboratory. This is to look at the upper body. This is an orthopedic issue. Many teenage girls and boys, they have scoliosis, right? And that is a deformity of the spine, right? And typically what happens is that if you think of the spine as a rod going between the pelvis and the neck area. Of course, it's not a rod; it's kind of it's a many degree of freedom system. But the typical curvature of the spine has been altered because of the disease. And the question is, how can we use this device to correct for it, understand the biomechanics of these? So we have created these spine exoskeleton, and in fact, there is a video of this on IEEE Spectrum if you're interested in looking at in more detail. And there are several papers that we have published. But we have these spine exoskeletons for men as well as teenage girls. And we have actually performed some studies. I'm going to show you some very preliminary work from these studies. So for example, this is a 3-segment device or 2-segment device. There is a pelvic segment, there's a mid-thoracic segment, there's an upper thoracic segment. And in between, this is a parallel robot. This is a 6 degree of freedom system, which can essentially position and orient that particular segment relative to the previous segment, right? So basically, you can take the middle segment and you can translate or reorient it with respect to the base segment, and similarly for the top segment relative to the middle segment, right? And the goal here is to understand how does the biomechanics of somebody with a scoliosis differs from healthy subjects. And this is, if some of you are not familiar with scoliosis, you can see this is an X-ray view of somebody who has got a lateral displacement of the spine, or somebody who's out here, which has got a hump or a hump on the upper body, and these are called kyphosis, right? And we want to understand what the biomechanic characteristics are. So this device allows us to do some simple experiments in terms of you apply a displacement, and you can know how much force you need to apply in order to sustain that. So essentially, you're looking at the force versus displacement, or some sort of a stiffness of the upper body among these groups. So we did a study with 8 female young subjects with age around 17 years or so. And these are scoliotic 8 subjects, about 30-year-old, to understand what kinds of differences are there. And there's a detailed paper that has appeared on in the IEEE Robotics and Automation letters, but that sort of characterizes some of these results here, and kind of shows what are the similarities or differences between the able-bodied people and those with scoliosis. So I'm not going to sort of, in the interest of time, I'm not going to go in detail out here, but I just want to refer you to the paper, and you're welcome to look into it. So this is the last segment that I wanted to sort of talk to you. This is about something called a wheelchair robot for active postural support, right? We call it acronym as RAPS. And the idea here is that many of the children or adults who are in wheelchairs, they of course have a very limited mobility. Of course, their legs don't work. That's why they're in a wheelchair. But also, while they're sitting on a wheelchair, they have got very little ability of the upper body to move around. And in fact, we did a survey of people who sit on a wheelchair and asked them, what exactly do you miss most when you are in a wheelchair? Okay, and maybe you want to sort of think a little bit about it. What would you miss most if you were on a wheelchair? Okay, and the answer from many of these people were that they are not able to pet their dog, right? And you may sort of think back, what is so important about dog or this activity? And if you think about it, I mean, by petting a dog means that you have to really bend down, right? Or in essence, I mean, these individuals are not able to bend down and do things that are there on the ground. So our goal was to create these robotic devices which can assist in daily tasks of these individuals who are in wheelchairs, and some of those. So I'm going to show you just a few quick video. This is a device, we call it RAPS. This is a 4 degree of freedom device. Okay, this base segment sits on the pelvis. This is on the mid trunk area. And the reason why I had actually 4 degrees of freedom, that was motivated from the fact that many of these wheelchair people, they actually develop something called a neuromuscular scoliosis, right? And scoliosis is all about kind of lateral curve of the spine or torsional curve of the spine. So we created a brace that does not allow those 2 degrees of freedom in order for us to prevent these wheelchair users from that. Um, so let me kind of show you just a video of somebody, in this case, he's not on a wheelchair, but he's sitting on a bench, but we're trying to understand what the human biomechanics is, what the muscle activity is during some of these movements, and how the robot can facilitate these movements if they're not able to do by themselves. In other words, you can sort of take them through a larger range of motion that they were otherwise not able to do. So this is sort of some of the work previously, but we are building upon this work also right now. So a few key takeaway messages. I hope I'm able to impress upon to you that robotics can play an important role in training and assistance. We showed you a few examples in the beginning that were related to training, right? And a few examples at the end, which were more in terms of assistance. And here we're looking at balance, posture, gait, right? Posture could be while you're sitting, or you could be standing, or you could be walking. And of course, I mean, robotics has been used a lot in terms of improving walking characteristics of people. Now, what is also very interesting here is that robotics should be designed to be function specific, right? Whether you're looking at the arm control or the trunk control or the leg control, you have to sort of somehow keep those functional movements in mind, and that will allow you to sort of design something that would be more effective for those kinds of individuals. And also the robots can allow us to ask some very basic science question and intervention question, and basically, unless you try new things, you would not know what is the impact of those things on the human life. So this is just an acknowledgement slide here with the group of individuals. Again, the group is, we have a large group, but this group sort of keep on evolving. These are some other studies where we're looking at these instrumented shoes for children with cerebral palsy, or there's another device that you can see on the left out here. This is sort of motivated from patients with spinal cord injury who are not able to stand because of the poor sensory motor control of these individuals. So we have a lot more applications at this time, looking at spinal cord injury, walking, gait, and function of some of these. So let me kind of stop here so that way I can give you some chance to ask questions. And let me unshare my screen here so that way we can sort of have a more of a question and answer format.
Yeah, so thank you, Professor Sunil Agarwal. So to the participants, if you have any questions, can you please write them in the Q&A? So participants, you can write your questions in the Q&A if there are questions. Yeah, so in the meantime, I do have a couple of questions. The first is that you are using parallel manipulators in several of your devices. How important is it to have compliance in such systems for safety, or what are the safeties that you think are mandatory? Or
yeah, I think that's a great question. In fact, most of these rehabilitation robots that were designed earlier on, they were all rigid link devices. So maybe some of the first visuals that you may think about are Locomat, right? I mean, these are leg training devices, and they are kind of bulky, and then they are very rigid. And what we're really talking about are people who are very vulnerable, right? They have a low ability, they have weak people, right? And you want something, first of all, you don't want to add, say, 30 kilograms to the mass of individuals. So if I'm 70 kilogram weight, you don't want to add a Locomat, which is 30 kilograms on me. There are several issues. I mean, first of all, it's very daunting, bulky, but also it kind of changes some of your muscular ability as well, right? So what you're seeing in the machine is not something that you will see over ground, right? Because when you're walking with the machine, you have this huge inertia that you added onto it. But when you're walking or you're trying to sort of see what is the outcome of that, you have to just kind of working with your own body, right? So you want these devices to be lightweight, compliant as possible, and so what we thought was that a cable device is really an ideal for something like this. So if you think about, let's say, the truss device or the T-pad device, what you're really doing is adding on 300 grams to the human body, right? And the wires, right? So what you really added on is a very small fraction of the human weight, right? So essentially, whatever you are seeing or observing in the individual or the patient, right, it's a reflective of their body, right? So that they can easily translate it to later on in the life. And again, these are all hypotheses, but that's where the motivation was for these parallel devices. And again, I mean, just to wrap it on, I mean, my PhD work was on parallel devices. So I have a lot of insights into design of parallel manipulators. And so that sort of allowed me to kind of pair my understanding into parallel actuated robots through the cable robots onto the human augmented systems.
Okay, thank you.
Thank you, Ashish.
Thank you. There is another question from Shushant. What are the safety systems put in place, more specifically at actuator level?
Yes. So of course, I mean, we have all of these vulnerable people who are kind of wearing it. So we have, I mean, whenever you put something on the human body, right, you want to make sure that the forces are fine or within a certain range. The motions are within a certain range. So we basically make sure from software point of view, as well as various kill switches that are around, both for the individual as well as for the engineering or the clinical personnel, so that way you have all of that safety. Yeah, I would sort of say that both the T-pad as well as the trust, they've had more than 300 people each as subjects into these devices. And touch wood, I mean, we have not had any single issue of any adverse effect or so.
Okay. So are there any more questions? Okay, if there are no more, yeah, there is a question. The actuator seems to be compact. Are they developed in-house or purchased?
Okay, so we purchase the motors, right? So the motor and the sensor and the electronics, of course, I mean, we purchase outside, right? But everything else, the integration of the system or the programming of the system, right? And the way the mechanics is designed, right? That's all designed in-house through simulation and so forth.
Okay.
Yeah, I see that there are a number of questions here in the chat. Yes, so maybe Ashish, if you want to sort of scroll down and read through them, I'm happy to sort of answer them as you ask them.
Yeah, you can answer them straight also, I think, because it's taking some delay to come to my system.
Okay, well, I see. It's going totally smooth for beginners.
So they were
okay.
Earlier session actually.
Oh, were they earlier session questions? Oh, okay. Yeah, probably it's from a different session.
Is different.
Okay.
Okay. Yeah. Because here I saw just 3 questions.
Okay. All right.
Okay. Thank you then, Professor Sunil Agarwal. It was really, what should we say, energizing for somebody to speak of mechanical design these days is very rare. You know?
Yeah. Well, thank you. I think we all have to be creative, and
Yes.
one of our goals is to be able to see how we can impact people and their lives. Of course, I mean, robots have made a big inroad into manufacturing and industry, but I think the human application still there is a long way to go, and hopefully Ashish and myself and other people in the audience are the ones who are kind of make that happen for people overall all around the world.
Okay, thank you then. Thank you very much for sparing your time early morning to come and make this presentation.
All right. Well, it was a pleasure. Thank you, Ashish and Vineet and Rajiv. I know that it was a little bit of daunting in the beginning to sort of get this all working, but thank you so much.
Okay, thank you, and bye.
Okay.
Thank you, sir.
Okay. Bye-bye. Bye-bye.
So all the participants, sir, you want to make an announcement?
Yeah, I will just, so today we have finished our session. This was the last session. So tomorrow morning we start off with the inauguration at 9 o'clock, 9 in the morning. So please be there. So tomorrow we officially start the AIR conference, the paper presentation and the plenary talks. Okay. So please be present by 9 o'clock tomorrow morning for the inauguration. And after the inauguration, we have the first plenary talk that is by Professor Ashada from the University of Osaka University. Okay. So we'll meet again tomorrow. And after the plenary talk, we have the first technical session. Then there is in the morning. Then in the afternoon, we have technical session 2 and technical session 3. Okay. So especially the speakers, please do come on time. Okay. And you will be given just 15 minutes for presentation as we are on online mode. Okay. So please come on time and come at least 15 minutes before your session. So if your paper is at, say, your paper is at 11:40, you should be there before the start of the session. Okay, please note that all speakers should be there before the start of the session. Okay, please don't come exactly at the time when you're going to make your presentation. Okay, because it takes us some time to bring you on stage and get your connection and things like that. So before the session starts, 15 minutes before the session starts, you should be there. Okay. Okay, so we'll see you tomorrow morning at 9 o'clock. Okay. Okay, thank you. Bye.
We'll meet in the venue.
Yeah.